Howdy everyone, welcome to the Chapter 11 tutorial video for our example problems. Today we'll be focusing mostly on the ideal gas law, but with the different ways that we use it. One, we'll just do a normal problem with it. Then we'll do a problem where we use the ideal gas law to determine the molar mass of an unknown gas. And then finally we'll use one where we want to do our three-step stoichiometry, but one of the steps gets replaced with using the ideal gas law. Alright, so let's go ahead and get started on that. There we go. So this one was from 11.65c. It says, what is the pressure of a 1.74 times 10 to the negative third mole gas sample if the volume is 28.5 milliliters and the temperature is 25.4 degrees Celsius? So I picked this one. This was one where it's, the book says fill in the table, but I just made one problem out of it. But I picked this one because it's got the extra work that we've got to say, wait a minute. Whenever we use the ideal gas law, so let's remind ourselves, PV equals nRT, we've got this R, we've got this gas constant where R equals 0.08206 liter ATM over mole Kelvin, and we've got to make sure our units match those. So we say, okay, we've got moles, that's good. Oh, but we've got milliliters. We've got to change that. That's not good enough. So go from milliliters to liters. We divide by 1,000. This will be 0.0285 liters. And then for temperature, we've got to be Kelvin. We've got to add 273.1, or well, 0.2 because it's 0.15 and it rounds up. So when we do that to that, that'll be 298.6 Kelvin. But now that we've got those fixed, now we're ready to go. So we'll say, okay, we want to solve for pressure. So I'm going to rearrange this to make it pressure equals nRT over V. And then we'll plug that in. We've got 1.74 times 10 to the minus third moles. That's an O. We've got R, 0.08206 liter ATM over mole Kelvin. We've got the temperature here, 298.6 Kelvin, and then all of that over the volume, 0.0285 liters. And then it's just plug it into the calculator. So 174 times 0.08206 times 298.6, and then divide it by 0.0285, and we get a pressure, which will be an ATM because of here, right? If we look, moles canceled, Kelvin canceled, liters canceled, we got ATM. The pressure with how many sig figs here? 3, it looks like. Well, that'll be 1.50 ATM then. So I got 1.4959, so yeah, 1.50, and there's our answer. So, that's a nice, simple, direct ideal gas law, but always watch out. Are your units the right ones? Do you have liters? Do you have Kelvin? If they gave you pressure, do you have ATM? All right, so now that we've got a quick example of just a regular ideal gas law, let's go ahead and use it for some other situation. In this case, to find the molar mass of a gas. And so they tell us a sample of gas is 38.8 milligrams. Its volume is 224 milliliters at 55 Celsius and 886 torr. What is the molar mass of the gas? And so the way I always think of this is say, okay, molar mass is just always grams per mole. So if I need grams and I need moles from something. Well, here's the grams. It's milligrams, but I can make that grams. I divide by 1,000. So this would, I'll just put it up here, 0.0388 grams. So, okay, I've got that number. But where do I get moles from? I get it from the ideal gas law. So if I have PV equals nRT, well, that means N is going to be PV over RT. So if I just plug these in, I can get N, and then I can plug N in right there. The trick is, again, it has to match R. So I look, do I have liters? No, I don't. I got to make this liters by dividing by 1,000. So that'll be 0.224 liters. I don't have Kelvin, I got Celsius, so I got to add 273 to that. So that'll be what, 328 Kelvin. And then for torr, that I got to convert to ATM. So I'll write this one out, that 886 torr. We would set up our little conversion, that it's 760 torr on the bottom for 1 ATM. So when we go ahead and divide that, 886 divided by 760, 3 sig figs, we get 1.17 ATM. All right, but now I've got my three numbers, I can plug them in. So I'll get N equals P, which is 1.17 ATM, times volume, so times 0.224 liters, over R, right, so over 0.08206 liter ATM mole Kelvin, great. And then temperature 328. All right, and then we've got it all set up. It looks good. We're going to punch it in. So that times 0.224 divided by 0.08206 divided by 328. That looks good. It's a very small number. It's 0.00, let's see, 3 figs, 970 I got, moles. But that makes sense because we have a very small amount of grams. There's a hint whenever you're doing this. Your molar mass always has to be at least 1, if not 2, because the smallest atom is hydrogen, and it has a molar mass of 1 gram per mole. So if you ever get an answer that's smaller than 1 when you do this final step, you're not right. Go back and probably check your moles. Maybe you typed something in wrong. But let's go ahead and get our final step for us. We got our molar mass is grams per mole. So we take the 0.0388 grams. We divide by the 0.00970 moles. And so when we type that in, 0.03388, right, it's 388, yeah. Divide it by 0.00970. Well, conveniently, it's not much bigger than 1, but it is 4.00. I got my calculator says 4 exactly. And a double check you can do it, sometimes for fun, is to say, is there a gas with the molar mass of 4? And it turns out there is. Helium. Helium has a molar mass of 4, so I guess this is helium probably. But there's our final answer doing this work. All right. There we go. So let's move on one last problem where we'll say, okay, let's take the ideal gas law, but let's do stoichiometry with it, where we talked about that in Chapter 8. There's always the 3 steps. Step 1 is get to moles. Step 2 is convert moles for what you want. And then step 3 is get to your answer unit. But here with gases, one of those steps, either the first one or the last one, is going to be replaced. Instead of a conversion factor, it'll be the ideal gas law because we got to plug in those other conditions. Remember, there is a shortcut. If you're at STP, then you can just keep it a conversion and use 22.41 liters per mole. But if you're not looking for liters, or if you're not at STP, then you got to do it this way. So we're given an equation here. 2 aluminum plus nitrogen goes to 2 aluminum nitride. And they want to know how many liters of nitrogen. Oh, I'm sorry, I should have written this down. This is 11.93 in the book if you want to go to your text and follow along. But how many liters of nitrogen at 892 torr and 95 Celsius are required to react with 18.5 grams of aluminum? And so, okay, the given here is aluminum. So we're going to start there, and we'll work until we find out, okay, where do we need the ideal gas law? Because when I see liters of a gas, I know I'm using the ideal gas law somewhere. But we'll start out with our normal stoichiometry. 18.5 grams of aluminum. I know to start with normal stoichiometry because grams, right? I'm looking at a solid here, grams of a solid. All right, so grams of aluminum on the bottom, moles of aluminum on the top. and we look up the molar mass for the periodic table, that's 26.98. Right? We'll then, that's our first step. Get to moles. Good, we're at moles of aluminum. Second step is to convert between moles that you start with and get to moles of the chemical you're interested in. So I need to get to moles of N2. Right? So moles of aluminum on the bottom, moles of N2 on top. Use the balancing, sorry for that mark there, 1/2. Okay? And then the third step would normally be, get to your answer unit, but that's where we say, well, wait, I want liters of a gas. I need the ideal gas law, and I'm not at STP. I can't just do times a fraction. I got to stop here. So I'm going to pause and just say, okay, let's get that answer. 18.5 divided by 26.98, excuse me, divided by 2, we find out that we have 0.343 moles of nitrogen. And we say, okay, that's great. How do I get to liters? I'm going to use the ideal gas law because we have PV equals nRT. And if we rearrange for volume, for liters, we say, okay, volume is moles, which we now have, times R, constant, times the temperature, that we have one, all over the pressure, which we have. Now we got to make them the right units again. So for temperature, we'll go ahead and add the 273, which means we're at what, 368 Kelvin there. For this, again, we'll convert that, so I'll write it up here. 892 torr times 760 torr on the bottom and 1 ATM on top. Let's see, what is that? 892 divided by 760. 1.17 ATM. Is that the same ATM as the last one? Yeah, I guess I guess they round about the same way. Interesting. Okay, so we have 1.17 ATM, and so we'll use these two numbers in our ideal gas law. So now we're just going to plug it in. That volume is 0.343 moles of nitrogen. I guess I could have just put it as moles. Let's see, times R, so 0.08206 liter ATM over mole Kelvin, times the temperature, so 368, and then all over the pressure, 1.17 ATM, and we just punch it all in to our calculator, so 0.343 times 368, and then divide it by the ATM, we get a volume of 8.85 liters of nitrogen. Let me clean that up so that it does not look like a decimal point there. There we go. But yeah, 8.85 liters of nitrogen, and that would be our final answer. Okay. So the ideal gas law has a lot of applications. It could be a straightforward question of just, find the missing variable, or it could be, we're going to do a bigger problem. You've got to use the ideal gas law to find something and then plug that in somewhere else, like we did with molar mass. Or it could be we find some information to be able to then plug into the ideal gas law later. But a very handy equation. Make sure you know it. Also, make sure you know the combined gas law. I know I didn't do an example here to try to keep the video a little bit shorter. But remember, if you have a beginning state, you have an end state, P1 times V1 over T1 equals P2 V2 over T2. Plug in what you know, cross multiply, find what you're looking for. But if you know those two gas laws, ideal and combined, you're really going to be well set for this chapter test and for using the material in the future. All right, so I hope this was helpful. Email questions, come in for office hours, see the tutors, whatever you need to do to get the help. And I will see you next time. Have a good day.